morning, everyone. So, in this fourth talk, we're now going to see how this whole messy, like finding explicit bases stuff actually helps us in computing algebraic K-theory. So remember, last time we had this chart drawn where I put basically Frobenius twisted prismatic cohomology in this case where my ring R is OK mod pi to the n, and my base delta ring is, oh great, is ZP adjoint, sorry, Witt vectors of the residue field adjoint Z. And I guess Ben yesterday explained to us that prismatic cohomology just makes sense in full generality if you just have some delta ring A and some A algebra R. And usually that behaves more like a version of absolute prismatic cohomology. So if A is, for example, ZP itself, it is what's called absolute prismatic cohomology. But in the prismatic case, so if the map from A to R actually contains some distinguished non-zero divisor in the kernel, so that there is a way to put a prism structure on A to make this look like relative prismatic cohomology, this agrees with relative prismatic cohomology. So I wouldn't have to specify this here, but in here there is like a distinguished non-zero divisor in the kernel. This like D equals an Eisenstein polynomial. Okay. And then, depending on the choice of this D and everything, we came up with some explicit generators here. And last time I ended with somehow analyzing where in the Nygaard filtration and another filtration that this thing inherits from the Z-adic filtration on my base delta ring and the pi-adic filtration on R, where everything lands there. And we saw that somehow powers of my distinguished element have higher and higher Nygaard filtration, but they're all in this F filtration 0. But then powers of Z land in higher and higher F filtration. And then these other generators, these F0, F1, and so on that land in here, these somehow went off along this diagonal. F0 was literally Z to the n, coming from the fact that somehow in R itself we've killed Z to the n. So in prismatic cohomology it has to be in higher Nygaard filtration. And then this had something like a deformation of divided powers on it. Like F1, there was some relation that we didn't spell out, but we could have, which is like F0 to the P equals something times F1 plus other stuff. So you get this staircase pattern, where here you, of course, also have something like ZF0 up until Z to the n minus 1, F0. And then there's like F0 squared, and at some point you hit like F0 to the P, but that's expressible in terms of F1. So along this line of slope n, we have like monomials in the Fi's where the exponents are all smaller than P, and everything is in this area under this staircase. Goes until Z to the n minus 1. And then Z to the n is F0, so that lands here. And that's like F0 squared. Then Z to the n times F0 is F0 squared. And last time I just gave you this picture as like heuristics in which filtration everything lives, and didn't make any claim about how independent or dependent these are. And this is not a picture of like a basis over the p-adics, for example, right? Because, for example, Z and D, there could be some linear dependence between these. In the case where we are not ramified, my Eisenstein polynomial could be something like Z plus P. And then I guess Z, like D minus Z would be P. So this is not independent. But remember, the Nygaard associated graded of the Frobenius twist is a free R module on monomials of the form some power of D times one of these monomials in the Fs where all the exponents are smaller than P. So the Nygaard associated graded, basically think about slicing this picture along columns. That's free as an R module on these guys. And another way to say this is that if you also take the associated graded with respect to the F filtration, right, that had something to do with the pi-adic filtration on R, this is a free K adjoint Z mod Z to the N. Right? This is the associated graded of the pi-adic filtration on R. Module on D to the C on these monomials. And of course, another way to say this, that it's a free K module on monomials where I also have some power of Z in there, where I guess the exponent of Z is smaller than N, and the E's are smaller than P. Right, so this bi-graded, where I've taken the associated graded with respect to both filtrations, that's free on those monomials as a K module. And now I can use this to infer, using that in the, if I take just the F associated graded, then in there, remember what the D was? The D was an Eisenstein polynomial. Z has positive F filtration. So modulo higher F filtration, this is really just the constant term of the Eisenstein polynomial, which is P times a unit. So in here, D is like a unit multiple of P. Let me write this with like a tilde symbol. And let me spell it out once. Unit multiple. And so what this basically tells you is if you take the F associated graded and then the Nygaard associated graded, you get a sequence of like K's in each of these rows. But this here tells you that the extensions there are non-trivial. So the associated graded is, with respect to F, is a free WK module on monomials Z to the A times FU to the EU. Right? So in other words, what I'm telling you is that if I just take the F associated graded, each of these rows here is just a single copy of Witt vectors free on whatever's here, right? Like the zeroth F associated graded is just free, like a free WK module on 1. The degree 1 stuff is free on Z, and so on. Then in here, we're free on F0, and so on. Maybe a little reality check exercise. There's actually a unique monomial of this form for every given degree with respect to this F grading or filtration. And that's because you can, here we have like powers of p appear, and you can like uniquely write every number as a sum of powers of p with coefficients smaller than p. So here we've used this F filtration, but this allows us to say something that strictly speaking, I wouldn't have needed this F filtration to state, which is we really have a basis for this Frobenius twist, like on the nose, without passing to any associated graded. Namely, these Fi's, we didn't just define these on the associated graded, right? These really came to us as elements in the Frobenius twist by applying these operations delta I. So what we learn here is that the Frobenius twist is a free WK module on all these monomials, z to the a times product of fu to the eu. And in fact, we get a little bit more, because imagine, like, what about the nth stage of the Nygaard filtration? Well, we know where that lies in the picture, right? In the picture, that's just everything lying to the right of like a vertical line at position I. And by the same observation, this is a free WK module on all monomials z to the a, d to the c, fu to the eu, with a smaller n, all eu smaller p, and c minimal with such that this thing has actually Nygaard filtration bigger or equal 1, right? And so what's the Nygaard filtration of such a monomial? The D is in Nygaard filtration 1. The F's are in Nygaard filtrations given by powers of P. So EU times P to the U bigger or equal I. So what does that look like in the picture? That basically means that, and now maybe let me draw like a zoomed out version of the picture, so we can really see just a qualitative thing. So the entire thing lies under this staircase. And then the Nygaard bigger or equal I part, we have colors, very good. That's the stuff lying to the right of some vertical line like this. So this area here, that's the Nygaard bigger or equal I part. And what I'm telling you is that we have a basis for both these things. For the full thing, the basis is just whatever monomials you see along the edge of this staircase, powers of z, then we have like powers of z times f0, and so on. And a basis for the Nygaard bigger or equal I part, that's given by also by kind of monomials to the leftmost edge of this thing. But these are now somehow, here I have like d to the I. But then, for example, here, to get f0 into Nygaard filtration I only need to multiply it with d to the I minus 1. And so these guys that I get along this edge here, these are a basis for the Nygaard bigger or equal I part. But crucially, what you should notice here is that that only makes a difference below this line here, below f filtration IN. Because above that, all of the monomials without the d's already have Nygaard filtration bigger or equal 1. So somehow the bases we chose here differ in this region, But up here, they start to agree. And what's the map that relates these to each other? It's the can map, right? The can map is really just including these into another. So if you want to compute what the can map does, you basically just evaluate each of these d. You just plug in the Eisenstein polynomial, multiply that out, get something that just involves z's and fu's, and maybe you have to kind of reduce modulo the relations we have to really get one of these monomials where you only have power like z to the something smaller n and so on. But what this picture tells you is that the can map is really an isomorphism on the f bigger equal in part. And this also already tells you that you can understand something like the order of the Frobenius twist modulo Nygaard filtration bigger equal I. So talk about that more in tomorrow's talk. What we want to observe now is more like a qualitative statement, namely that a lot of things just agree rationally. Let me state the following corollary. So let A be WK adjoint Z as before. But then let's look at all the OK mod pi to the n. So here I'm fixing OK, right? I've decided what my residue field is. I've decided what my Eisenstein polynomial is. But I can, of course, truncate this to different lengths. And I'm also allowing OK itself. Think of this as like OK mod pi to the infinite. So in this case, we haven't discussed this explicitly, but you get the same kind of picture where the staircase just has like an infinitely high first step and no further steps, right? You really just get the same picture with just powers of z. And then the following maps are what we call filtered isogenies, by which we mean they're rational isomorphisms on the f associated graded, and hence on every finite portion of the f filtration, right? If I have a filtration, instead of just taking the associated graded, I can also do something like take f bigger equal a modulo f bigger equal b for some larger b. Let me write this as f to the ab. Sorry, by that I mean f bigger equal a mod f bigger equal b plus 1. So the thing where I only have stuff from degree a to degree b inclusively. Right. So filtered isogeny, by that I just mean rational iso on at least finite stages of this f filtration. And one thing we saw over there is that this is true for the map can from Nygaard bigger equal I, the Frobenius twist. And this is true for each of these Rn's, including n equals infinity, where I just include this into the full thing. And of course, this also tells you that the map from any stage of the Nygaard filtration to any other stage of the Nygaard filtration has this property. And that's just expressing the fact that on the f associated graded, this is really like an inclusion of something free on WK into something else free on WK, and the multiplication is by some power of P. And which power it is basically just how wide the gap between the staircase and the cutoff thing is in that row. Right? So that's nice to know. The other thing is you can also ask what happens if I map between different of these Rn's. For example, from OK to OK mod pi to the n. And we get the same statement. The canonical map between two different of those also is such a filtered isogeny. I've just explained the first part. For the second part, note that it's sufficient to do this for m equals infinity, right? Because otherwise you have like three things, and this is obviously something with a 2 out of 3 property. And for OK, you have something where the basis is just really given by powers of z. Over here, you have these monomials in z and the fi's as basis. And so all you need to do in order to check this is you have to figure out what happens to something like z to the k for some number k if I express this in terms of this basis with the za times f to the times this product of f to the e, in such a way that here the exponent on the z is smaller than n, and so on. So you use some relations here, right? You rewrite z to the n as f0. That allows you to kind of reduce the exponent on the z down to down to something smaller than n. And then you might obtain some large power of f0. But then remember, I told you that these form something like a divided power algebra. You can explicitly, or I guess at least recursively, compute these relations, and you can deduce enough about these to know that on the f associated graded, this really behaves like a divided power thing. So in other words, what you get is, if you have some large power of f0, like f0 to the p still becomes like some rational multiple of f1, and so on. So if you do this, then this goes to some non-zero multiple of this, and then plus like stuff of higher f filtration. So say this is like literally true on the f associated graded, and then and in fact, if you think about these divided power relations, you can even say what like the index is here. So we could say something about how the co-kernel looks like on each f associated graded term and so on. But what we care about for now is just this is a rational isomorphism on each finite stage of this f filtration. So that's cool, right? Somehow this tells us that even though something like OK mod pi to the n is of course completely torsion, this prismatic cohomology is torsion free and basically just differs from the OK case by some weird denominators. So P. Yes, rationally I just mean invert P. Right, these are modules over WK. I can invert multiplication by P. Yes, so this is not, you could maybe also think about this as an A module and try to invert other things, but then you would maybe lose the filtration, right? Yeah, just want to invert P. Yes. Including m equal infinity, and it suffices to check that case because then OK maps to everything. And that's very useful because in the m equals infinity case, formulas become easier because there you only have to think about powers of z. You don't get these divided powers fi. So now we've seen somehow how we can explicitly touch this relative prismatic cohomology. But what we actually want to compute is, as Ben told us yesterday, we want to compute absolute prismatic cohomology, right? So what Ben told us is that in terms of absolute prismatic cohomology, you can write down these symptomic complexes as fiber of can minus phi. And those are the things we care about. Those are the things that under some kind of motivic filtration on TC correspond to the associated graded. And since K-theory and TC can be compared very well in this case, I think Ben mentioned that yesterday as well, that's the thing we want to compute. And so how does this relative stuff relate to the absolute stuff? So Ben also had this on the board yesterday. So this is heavily inspired by work of Liu and Wang. They did something like this directly for TC of OK. And their idea was there's an absolute TC, and that's the thing that has something to do with K-theory. That's what we care about. But there's also relative TC, similar to this relative prismatic cohomology. And so they wrote down some cosimplicial diagram where if you want to get from the relative to the absolute thing, one thing you can do is you can write down some kind of Čech nerve where you just work relative one variable, and then you work relative two variables, relative three. All of these go to the same element, pi and r, but they get some description of the absolute TC as a limit of that. And right, let me also say something about that in a second. So the thing we studied above there is working relative WK. Will turn out that will agree with this because WK is like the cotangent complex vanishes. Yeah, it's formally étal over ZP. But so this is the thing you would try to write down if you like when you read this Liu Wang paper and you're like, okay, they can do something like this in TC. Can we do this in prismatic cohomology as well? And then there are multiple problems. One of which is maybe my R is not actually an A mod I algebra for any prism structure here, right? Over here we needed the WK. My Eisenstein polynomial might have coefficients in WK and not just in ZP. But there's a more crucial problem, which is even if this is just a ramified extension of ZP, if you can choose some Eisenstein polynomial in here, surely this is not going to be sent to the same thing under both of these maps, right? You pick some Eisenstein polynomial Z here, but then this goes to EZ0 and to EZ1. So there is no way to, even if you can put like a prism structure on this guy to make sense of this, you can't really put a prism structure on this guy in such a way that you get both of these maps. So in order to even write down this diagram, you need this additional factoriality that Ben talked about yesterday, that prismatic cohomology really extends to a functor on this category of delta pairs, where objects are really just given by a delta ring A and an A algebra R, no conditions on having some chosen ideal such that R is an A mod I algebra, nothing like that. You just forget the prism structure, just remember that you had a delta ring and a ring, and prismatic cohomology still makes sense in that generality. So that's the world in which this diagram lives. But then you can prove some things. For example, you can prove that if you take some formally étal extension in the base, that doesn't change anything. So this also agrees with that. And you can also prove that if this is like a prismatic delta pair, a delta pair where there exists a distinguished non-zero divisor in the kernel of the map from A to R, then this actually agrees with the thing that we discussed so far with the relative prismatic cohomology in the sense of Butt and Scholze. So to write down this diagram, you need more. You need really this prismatic cohomology relative delta rings. But then to compute everything except for this term, all of these, you're actually again in this Bud Scholze situation, where like this, but also something like this, you can write all of these as prismatic envelopes with the added subtlety that somehow, in order to write down stuff like the basis we did there, you really need to choose such a prism structure, and you need to think about how your descriptions for this differ if you choose one or the other, because somehow one of these maps will really be like the obvious one, and then the other will be more complicated. So that's the situation we're in. And so now I'm usually just going to write prismatic homology of R relative ZP adjoint Z, but keep in mind that you can replace this ZP by the Witt vectors, and then this is really the thing we've discussed so far. Yeah. Mm-hmm. Mm-hmm. Right, so combining two things. One is that this generalized version, this is really like a relative version of absolute prismatic cohomology, which is like horrible to say. We're not calling this, maybe we should just call this cohomology of a delta pair or something. But in any case, so first of all, this is like invariant under passing to a formally étale extension in the base. So in other words, if you have like two delta rings, A and A prime, and R is an A prime algebra, then these agree if this is formally étale. So that allows you to plug in like Witt vectors instead of ZP over there. And then also, if this pair A comma R is prismatic, meaning that there exists some ideal I such that A comma I is a prism and R is an A mod I algebra. So I need to find some distinguished element, distinguished non-zero divisor in the kernel, basically. Then this agrees with the thing we've discussed so far. And let me, for emphasis, I guess Ben wrote something yesterday where both sides were just equal. Let me write this like this, where here this is like prismatic cohomology really relative to this prism. That's this thing that's like a priori defined for delta rings. But these really agree. So if you can choose such a prism structure, then it's just the thing we discussed so far. And to get concrete formulas, you choose one of these ideals, but then here you have to think about how the generators we get differ under change of the prism structure. All right. So that's the thing we care about, and more generally, we maybe care about the Frobenius twist and the Nygaard filtration because we want to get at these symptomic complexes. So let's put these in the picture. So this prismatic cohomology relative delta rings, I can also twist along the Frobenius on the base delta ring. Pleasantly, this doesn't do anything to the absolute case because the Frobenius on ZP is the identity. But let me still put this here. Yeah. Yes. Yes. So I'm saying this diagram exists, and it's a limit diagram, and it's also a limit diagram with the decorations I'm putting there now. So yes, this is a limit diagram. It's also a limit diagram if I put the Frobenius twists. And it's also a limit diagram if I put the Nygaard filtration. And so what we want can now be summarized in this large diagram. So what we want, as Ben explained to us yesterday, is the fiber of the can minus phi map here. There was another twist, this Breuil-Kissin twist. Just bear with me on that. What we have understood so far this entire week is these things in this prismatic case, where I can really write the R as a quotient of A mod I for some prism structure I. We've understood that particularly well in the case where it's like a regular quotient. I guess more generally there are descriptions if you're just like an algebra over A mod I, but in this regular quotient case we really found like a basis. And so instead of directly understanding these two terms, we should be able to understand all of those. Z0, Z1, and then it continues. And there are, of course, also can minus phi maps everywhere. And I forgot this twist here. The phi interacts with this twist, so I have to put the twist here, but I'm going to tell you something about that later. So we want this complex. That's this ZPI of R, this symptomic complex that filters TC. What we can compute are somehow the terms in these two cosimplicial diagrams. And each of these rows is like a limit diagram. So I can compute this entire complex as the total complex of this, right? Each of these here is just a discrete or maybe static thing. It's like it has just pi 0. It's really like a thing from ordinary algebra. We have bases for it and everything. So this cosimplicial diagram here really just you should think of as a cochain complex. And then we also have these vertical maps, and just take a total complex of that. The statement that the rows are limit diagrams is equivalent to say, or implies that this complex is quasi-isomorphic to the total complex of this. So that's nice and all, but now this is infinite in almost every direction. I mean, except the vertical one, but somehow it goes infinitely far to the right, and each of these guys we have a basis maybe, but it's like infinite, it's indexed over all kinds of stuff. So how do we control this? So there's two things that we can do to it. The first observation is what Ben told us yesterday, that absolute prismatic cohomology of R equals OK or OK mod pi to the n is concentrated in homological degrees -1 and 0. So although these are really complexes, these are not just concentrated in pi 0 and sort of ordinary algebra things. They're not that bad. They only have like an h1 and an h0, like h upper 1. So in other words, that means that these cochain complexes that go on, like these two rows that I just drew, these really have to be exact, starting with like degree 2 and higher. So we may replace the degree 1 term in each row by cycles. and just discard the rest, right? That's something, if you know what range the cohomology of a cochain complex is concentrated in, you can just truncate it by putting cycles in 1 degree and then just zeros after that. So then we get a new description of this, really as total complex of just a square. Let me put this here again and start a new piece of chalk. So here I have this relative term, and like the Nygaard and the other thing, here I have can minus phi. And then here I have to put something, and it's the kernel of the like alternating sum of the 3 maps that go out there. So let's just give that a name. Let's call it Z. And to remember what we're talking about, let me put these decorations here. So let me just write this as Z twist 1 and Nygaard bigger equal I Z twist 1. But this is really defined as the cycles in degree 1 in the corresponding complex. And this map we can still think of as can minus phi, but it's somehow, I mean, the kernel version here. Okay, so we get this square and some mysterious differential here. Yeah. There are twists missing, yes. Sorry about that. Let me also put these here maybe. Yes, there's a Roykissen twist missing. That's a little lemma you can prove, that if you have a chain complex and you know that it's like a cochain complex and you know that its cohomology is concentrated in degrees 0 to n, it's quasi-isomorphic to the cochain complex where in degree n you put the cycles and beyond that you just put zeros. It's also the n truncation in like the Postnikov T structure on chain complexes. Or minus n. Right. So that's one observation we can play. And then the other is that on filtration bigger or equal n, as we saw earlier over there, everything here, also these things relative multiple variables, all of that lives beyond, like below that staircase. And so on f bigger equal n, the can map is an isomorphism. Right, so if I apply f bigger, like all of this is still filtered, if I apply f bigger equal n to both the Nygaard bigger equal I term and the not Nygaard term, the can map is an isomorphism. Since also the Frobenius takes f bigger equal k to f bigger equal pk, right? That was what came out of our definition of what it means to have a filtered delta ring. The Frobenius should really dilate the filtration by a factor of p. It strictly increases filtration. So in other words, up to that filtration, can minus phi is also an isomorphism. On f bigger equal n. And maybe you have to be a little bit careful about completion. Turns out that completing with respect to f is equivalent to completing with respect to n because of this staircase pattern, and we're already p-complete. And the symptomic complexes at least don't depend on whether you Nygaard complete everything or not. So let me leave this like here. In general, you have to think about that a bit. But this means that the vertical maps are somehow isomorphisms beyond f filtration n. So there's a huge part of the spaces and everything which just does not, we have the better one, which just does not contribute anything. Think of that f bigger equal n part as just a huge acyclic subcomplex of the total complex. Yeah. No, I'm saying one map is an isomorphism and the other strictly increases a filtration. So this map can minus phi is an isomorphism on the associated graded still. I'm somehow perturbing like an isomorphism by something very small. And so we may replace the diagram by the thing where we've, messed up my own indexing. It's f bigger equal in, right? It's what I wrote up there. Saying this stuff here. In this stuff here, the red part and the non-red part line up, and can minus phi is an isomorphism between them. So we may replace the whole diagram by the diagram where we've just truncated away the large filtration stuff. So we may replace the whole diagram by f0 in minus 1, n bigger equal I, prism 1. And now let me drop somehow some, maybe not. Well, let me drop the indices. N bigger equal I, z1, twist 1, f0 in minus 1, and then here f0 in minus 1. And f0 in minus 1 z1. Twist 1. Right, I've just truncated away the part of the square where I knew that the vertical maps were isomorphisms. And so we can do that without changing the quasi-isomorphism type of the total complex. And there's one more trick you can play, which we also know what the 0th graded piece of this whole complex computes, namely the 0th graded of the resulting filtration on the total complex, on like the ith symptomic complex of OK mod pi to the n, really computes the ith symptomic complex of just the residue field, because that's the 0th graded part of this guy, right? You're getting rid of all the z stuff and all the fi stuff and all of that. You're just remembering something that you would have gotten out of thinking about just k itself. And this is 0 for I bigger 0. And I guess it's like zp in degrees 0 and minus 1 for I equals 0, but we just care about positive weight. So this tells you, right, since the graded 0 part vanishes, it tells you that you can even just take degree 1 to degree in minus 1 everywhere. So what we're looking at is basically just, in my diagram, the stuff between 1 and in. And now, we're lucky, right? Because we now know that this thing is now really a free WK module. Or let me write this over here. All terms here are free WK modules on in minus 1 many generators. Here we've described those, right? Here these are like z, z squared, and so on, and then these monomials in the z's and the f's. Here we haven't yet described them. No, sorry, here we also describe them. Here they're the ones where the same monomials, but you have to insert some power of d to actually have them land in Nygaard filtration. We haven't described them here. Notice that abstractly you get this also from this observation that the horizontal maps, like the fibers along the horizontal maps, are these symptomic complex, are absolute prismatic cohomology, and for some other reasons you can show that that's torsion. But in fact, so let me say something about these terms in a second, but let's just maybe breathe and realize what we've achieved. We've produced some really like finite type complex, or not even finite type, right? This is like really a perfect complex of ZP modules. There's a subtlety here, which is we've described all these as WK modules. Not all of the maps are WK linear, right? There's a can minus phi, and the phi acts on WK by the Witt vector Frobenius. So it's maybe better to view these as free ZP modules on F times in minus 1 generators, where F is the residue field degree, the degree of little k over Fp, which is finite. Yes, now we really have to be in this finite p-adic number field setting. But what we've achieved is we've really given like a finite description of this symptomic complex. And over here, this is very explicit now. Over here, this still requires some additional tricks, which basically amount to thinking a little bit more about the case where I'm relative two variables. Right, if I want to write R as a regular quotient of ZP adjoint two different variables, I can do this by writing OK mod pi to the n as WK adjoint Z0, Z1 modulo some choice of distinguished element, like the Eisenstein in the first variable, the relation that ensures W, like pi to the n equals 0, but then also I need one relation that identifies Z0 and Z1. And so we don't really have time to talk about this in more detail, but this also, of course, leads to a prismatic envelope description. And this will not only have this sequence Fi of generators that somehow come from this relation, it will also have another sequence of such generators that come from this relation. And there's a somewhat non-canonical trick, which is really to write down that basis and then define a certain map out of here, which basically arises as a certain dual basis elements, or a certain map that takes like the first of these basis elements to 1 and all others to 0, to actually identify this with a shifted copy of that. So this will be identified with f from 0 to in minus 2 of n bigger or equal I minus 1 of prism 1 I. And then we think of that as like a free module on some element you could call nabla z. And the shift you could interpret as nabla z living in F filtration 1 and Nygaard filtration 1. And I want to stress that this is a bit non-canonical. We really have to choose this like sequence of generators that we defined in terms of the z0 minus z1. So I don't actually know whether the notation we suggest here is actually super well behaved. That like this can really be thought of as some kind of twisted thing, and then maybe this as some kind of connection or so. It looks like that in the formulas, at least up to f associated graded. It seems a bit non-canonical. But with that additional description, we really get a diagram, like a square, where we have these ordinary terms, where I've explained bases for you. We have the maps can minus phi. And then over here we have this thing we call like the nabla term. And we also have some can minus phi on there. But the phi really is not compatible with writing this as a module like this. And also the horizontal map is not compatible, like it's not a module map. So the phi is kind of twisted in a way. But I can now quickly summarize for you what now goes into actually turning this finite description into some algorithm. And I mean, we've implemented that, and I think we should show it in the TBD afternoon slot. You can really turn this into a program that you tell, like, I want to know some k group of z mod p to the, like, z mod 2 to the 3, and it just spits it out after computing for a while. And so how this goes is all terms in sight, and most of the maps, like all terms in sight are free ZP modules of the same rank, and most maps are actually filtered isogenies, or like on this finite strip of the filtration, they're really rational isomorphisms. So the idea roughly is, first you compute the square of like the Nygaard bigger equal I prism 1 term. We drop some of these twists, but of course there's still a twist here. Of this term, of this Nygaard nabla z term, and of this nabla z term. You compute this, but for OK relative blah. Right? We've discussed this for OK mod pi to the n, but of course you can also do this for OK. And we only need this in some finite range of the F filtration. So we need it in this range from F1 to IN minus 1. You could, of course, compute this for an even bigger range, because, of course, there's no n here. So if you've computed this through a long range for OK, you somehow can share this result between like OK mod pi to the 2, mod 3, and so on. But so we compute this square, and that's somehow about working explicitly with these bases. And there's some tricks you can already play there. For example, this nabla commutes with, like the can maps are kind of obvious. The nabla then commutes with the can, and you can use that the nabla is an isogeny and the can is an isogeny to invert some matrices rationally and obtain this nabla from that nabla. You can then play a same game to obtain this phi prime, which is kind of mysterious, from phi, nabla, and nabla. Because again, all these maps are isogenies. Rationally, they're invertible. So we compute this for OK. And then the second part is we use that the maps induced by OK mod to OK mod pi to the n are filtered isogenies. to transport the maps to the OK mod pi to the n case. Right? So the trick that appears multiple times, so this can be used over there already, but also here, is that if you have a square of matrices over like free ZP modules, and you know that they're rationally invertible, then you can, if you know 3 of them, you can just compute the 4th one by using like the rational inverse, and like n by n matrices over ZP, of course, lies injectively in n by n matrices over QP. So if you can do this rationally, you have found the matrix over ZP as well. So this isogeny trick is super useful here to somehow reduce the work. And let me stop here. Yeah. So the question was, when you run this in practice, when does it become unbearably slow? And I guess we can't fully answer that question yet, because the way this project was that at the beginning we were like super excited and hacked together some very bad, like unoptimized Sage code. And then once this was running, and I think it, like we have tables for especially p equals 2, where I think for Zmod 4 we went all like to something like K30 or 35. And then if you increase the n, it of course also scales in that. So the other columns in our table are a little bit shorter, but something like Zmod 8, we still go to degree 20 and stuff like that. But I can't tell you yet what kind of the frontier will be, because I think there's still a lot of things we can do to optimize this severely. So but we also had some computations that ran for like something like 8 hours and then finished. Not sure what these were anymore. But the funny thing is really like all of the work is behind like manipulating these monomials, right? I mean, the way you would compute with this in practice is you first have to kind of make a list of these divided power relations. These are obtained by recursively applying delta and expanding this out. And then once you have those, all of what you're doing when you compute like a matrix for can or something is that you take one of these basis elements, map it into the other thing, and now you have some unreduced monomial. You have to reduce it using that. And a lot of what I still think can be improved severely is the way polynomials are handled in our current code. Somehow Sage does not really have a library to treat like filtered polynomial rings efficiently, where you only care about multivariate polynomials up to a certain filtration. But the fun thing is it spends like 8 hours like churning on these matrices, and then it's like 200 milliseconds to compute the cohomology of the complex. So like all the work is really in this manipulation of the polynomials, and I think that can be optimized quite a bit. But that's going to happen after we put a preprint on the archive. Yeah. Right. I was gonna talk a little bit about that tomorrow, because there are some apparent patterns. And I mean, some of the patterns that I will talk about tomorrow are very quickly explained. There's some kind of Euler characteristic thing. So what you'll notice is, I mean, this leads to a 3-term complex, right? If you take the total complex, but since like the maps are rational isogenies, sorry, not right, like these are like these filtered isogenies. So this leads to the fact that somehow H0 is trivial and the rest is torsion. So this is really 2 torsion groups. And the quotient of those orders has a nice explanation. The quotient of those orders really looks like in your, like the order that comes out in your computation of the crystalline case. And I'm somehow skeptical that there's a good explicit description of the actual group structure of the odd degree groups that come out there. But the even degree groups, the stuff that doesn't show in the crystalline case, those surprisingly are like often 0. That's what I want to talk about tomorrow. But they're also always cyclic for some reason. We don't know why. We don't have a name for the thing that seems to generate them. But I think parts of that could definitely be explained better than what our proof of this even vanishing thing currently gives. A full description, maybe. I mean, you asked me about this. There's like this formal group story of Drinfeld. It could be that somehow the things that, like you have an explicit formula in this FP adjoint Z mod Z to the N case as like co-kernel of Verschiebung on the big Witt vectors. Could be that there's some kind of deformed version of big Witt vectors that makes this work on the nose. I'm not sure. Currently, I don't have a guess about an explicit formula beyond that. Right. So if you just care about size, we can give you something even better than asymptotics, because as I mentioned, these are like typically just like 2 finite groups, and there's an exact formula for the quotient of their orders. But also, this is this thing that I want to talk about tomorrow, surprisingly, even though the even groups are non-zero in low degrees, if you go out far enough, and how far you have to go seems to be exponential in this number n. If you go out far enough, they become 0 again. So beyond a certain point, we have like a closed formula for all the orders, because the odd guys are just as in the Hesselholt-Madsen discussion of like FQ adjoint Z mod Z to the N, and the even stuff is 0. Before that, yeah, depends on how well we can understand this phenomenon that the even part is cyclic. Maybe there's an explicit description of the generator and which power of it is 0. I'm not sure.